So thank you very much for attending this late session. So I would like to start my talk about questions. Do you think, guys, there is a technology that enables fast computation with minimal energy requirements? So I will try to address this question in my talk today. So my talk will be around a new technology, we call it neuromorphic, and this is like human-inspired, has two elements. One of them, the sensing part, which is similar to the eye, and the other one, of course, the processor, which is similar to the human brain. Let me go first of all about the current limitations of the technologies and why neuromorphic technology is needed nowadays and in the future. First of all, regarding the limitation of the challenges of the computer vision lies on the following. We have, first of all, motion blur, and most of you, when you try to take picture, for example, while you are driving, then this is the motion blur we have. And this is explicitly due to the exposure time is not short enough in those vision systems, and this is what we have. And similarly, when you drive and you have the sun in the field of view of the camera, then you will have also certain issues. And this is also due to what we call it the dynamic range. The third one, it's about the trade-off between the latency and the bandwidth. So in computer vision, you have two choices, either to have high frame rates, therefore high bandwidth, you need more processing time to do, or the vice versa, and you will lose certain information. So those trades-off also, they are contradicting, but there is a technology to solve this properly. So let me go to the first part, which is the brain similar things, which is the processor. We have in conventional, like processors, they are GPUs and CPUs. So in those processors, frankly speaking, most of the energy goes because we transform information or transfer information from memory to processor and back from processor to memory. And this will consume high energy. Now, about the quantum computing, it's futuristic computing suitable for large scale like simulation. Now, what about neuromorphic? In neuromorphic computations or computing, it has low power consumption, less need for computational capability or capacity, and it can be used as a wide range in IoT and end devices and also mobile systems and other applications. It is bio-inspired. If we look to this B, it has only about 10 hertz speed of the processor or the brain, and the energy about 0.1 milliwatt. Having said that, it has the capability to do a lot of tasks more than systems. They have more capacity than this one with million times. So this type of technology, it is the neuromorphic. Therefore, we have to understand what is it and how we can utilize this one for what we want. Now, in terms of course, we are using this as exchangeable definition between neuromorphic and events. So when you hear event-driven or neuromorphic, it's the same definition. If we come to the sensing, we have the following, which is like imitating a human eye. Only we focus on the dynamic information. Therefore, there will be less volume of data. The other things, it is more adaptive for environmental changes, i.e. like the light intensity changes. The same things, it's continuous sensing. There is no interruption as we have it in conventional vision system as frame rates. Similarly for the processor. The processor is multimodal in terms of spatial and temporal. At the same time, also it has sparse, which is parallel computing, and it has less energy consumption. Now, if we look to this scene here, we have in the right, this is how neuromorphic system or vision system will see this picture, only focusing on the dynamic information, without focusing on the background information as we have it in conventional vision system. Therefore, you don't have to process all of these pixels, only you process those pixels where you have the dynamic or the motion. Therefore, you will have much less data and fast computation and this energy consumption in this case. And similarly, we're using spiral networks or SNN, which is spiking neural networks, as a parallel fashion of computing. Therefore, we have the data 3x less and the computational efficiency more 10x's as a rough numbers for this type of technology. Now, SNNs and innovation, they are pioneering. It's one company pioneering in this technology. They have reduced a camera plus the neuromorphic processor at 1 centimeter by 1 centimeter size. And this gives you where the future for this technology. Now, if you look to the autonomous cars, as we move from level 3 to level 4 and level 5 in terms of autonomous cars, we need, of course, more processing for the data we acquire from high frame rates camera. Now, there is a trade-off between what we call it the bandwidth and between also the latency in this case. So either in computer vision, we have low latency, then you have high bandwidth, therefore you have more data to process, and you have to wait for longer time in autonomous cars in order to predict pedestrian if the car moving at fast or high speed, or to have low latency, high latency and low bandwidth, therefore you will do computation fast, but you miss a lot of information between the frames. Then again, the car will hit the passenger because it cannot see between those frames of the images. Now with the neuromorphic, we have both of them. We have low latency and low bandwidth, i.e. it can predict in microseconds and it can act in very short period of time to avoid colliding with the passengers. As we can see in this, for example, part, how the neuromorphic see continuous changes of the human while he or she crossing the road. Therefore, there is a feedback for the car in order to stop or to change its direction to avoid any colliding with the pedestrian. In contrary, what we have here, we have more computation needed, or here more data will be missing. Therefore, you will not get what you got from the neuromorphic. This is a new advancement in terms of multi-bit pixels events, where again, the innovation sense company, they have developed a new technology in order to minimize the pixels and to reduce significantly the noise. This led, of course, to use this technology in order to have iris authentication or to observe the drivers while they are driving about their conscious, they are sleepy or something like this in very short period of time at minimal energy requirements. Again, this is also, it has a future for virtual reality, augmented reality. If we have these systems, they will consume less than 1 watt energy and they are compact in terms of size. So this is what we are proud of at Khalifa University, where I am from. And I am the director of the Advanced Research and Innovation Center. And we are one of the pioneering centers worldwide in a neuromorphic technology, especially or specifically about perception and deploying solutions. So in this here, what we have a neuromorphic touch type things where we can reconstruct the small changes or small indentation, in this case less than 0.1 millimeter at fast speed, which is around 60 centimeter per second. So the video, what you see here, it's speeded down about 1/10x. Now, why this is important? Because we can inspect the large surfaces. If we have, for example, wing of aircraft, tail of aircraft, and we want to inspect this quickly to see if there is a cracks or indentation within the tolerances of 0.1 millimeter, you can know this one immediately with this technology at high speed. While the current technology, you have to go from place to place to do this indentation to get this type of inspection. So this is one of the first results ever produced worldwide. It has been produced by Eric at Khalifa University. The other things has been also achieved by my colleague, Professor David Scaramoza from ETH Zurich. And what he has done exactly here, he took 20 frame rate like camera. As you can see, we miss a lot of information. At the same time, he took the event camera results here for this scene. He upsampled the low frame rates using events in order to achieve this marvelous results at the memory footprint 1/40. And this is maybe transition between classical vision to hybridize both, like conventional vision with the neuromorphic, but what we are looking for to implement only events in the near future. So the other application we have deployed to the production line of 787 Boeing aircraft at Strata production line, inspection of the countersink hole, as we can see here. So classically, what they do, they inspect each hole, and it will take sometimes between 5 to 6 seconds. With our neuromorphic solution, and this is real time, exactly real time now what you are seeing, real time inspection, we inspect those holes at 1 meter per second speed. I.e., if we have a wing, 37 meters with 4 rows, less than 2 minutes, we finish the task, while it takes hours by the conventional way. There is return on investment in this project only, in 5 years, $2.4 billion if it will be fielded for all the inspection of Boeing aircrafts in the production line. So this is what also we are proud at Khalifa University. We do research not to shelf it on the shelves. We do research to do impact and to contribute in the knowledge-based economy and to solve outstanding problems, niche problems, they are not in the market. The solution, what we produced, 10x faster than any state-of-the-art like solution available in the market today. This is also results to show how a neuromorphic vision system can work at normal lighting condition. This is from Zurich University, from my colleague David Scaramouze, and during low light conditions. So this is due to the high dynamic range. Therefore, this type of vision system can work during normal light condition as day conditions and also during night conditions. I tried to give different examples from different universities to show you the potential of this technology worldwide. Now, about the autonomous driving, if you look to that diagram over there, this is where we are today. And if we go beyond 26 to 2030, this is level 4 of autonomous cars and level 5. And if you can look here about how much bandwidth gigabyte we need per second. This high demand imposes, of course, you need high processors in the cars. And as a consequence, it will be high cost. And as you know, this vision system with a processor, it shouldn't contribute more than 2% of the overall cost of the car. With the current technology and the normal vision, this is impossible. But in neuromorphic, you will achieve this one and less cost and also better computation because you don't need this type of bandwidth in this case, and it will be fast computationally due to less data. Why? Because you are focusing on the dynamic information where there's a change. Anything doesn't change, you remove it, you don't process it again and again. So where we are today and what I want to believe for all the research community, for all the VCs, for all the companies to come together and to develop this technology further. In terms of sensor or vision, it's quite developed one, but in terms of a processor, more efforts should be put in order to develop this technology further. We have SNNs, now they are leading in this. We have Intel, we have IBM, but we need also more players to play in order to develop the processor of a neuromorphic processor in order to take us to the next stage. Next stage will be for mobiles, for edge devices, for IoTs, to use them also in healthcare technology, in autonomous cars, and other type of application. With this, I finished my talk, and I hope at least now you get what the neuromorphic computing is about and what we are doing at Khalifa University, specifically at ARIC Center, and how this field will evolve from here until maybe few years. The report appeared a few days ago. They're estimating from 2030, there will be revenue from this technology around $30 billion per year. And we hope that we are the major player in this technology. Thank you very much for attending this session.